So where we're going to start is with this question from the smart work, because someone asked about it. So this becomes kind of a more challenging question because what's happening here is you're being asked to effectively think backwards. So we want to know what the reactants are that make this final product. Okay? So when we see this molecule, what we need to do is start or any molecule, we need to start focusing on where there's chemistry and where there isn't chemistry and how we could start to put those individual pieces together. So when we go through and look at this molecule, where should our eyes first go? Okay. I think looking at the nitrogen is a phenomenal place to start. Okay. The nitrogen, being an electronegative element, is going to create a polar covalent bond, which is going to create some chemistry. We could finish it. We could even add the lone pair electrons out there. So we could see that as a source of electrons. Okay. If we're trying to make this compound, what we now have to do is backtrack out the new piece. So if the nitrogen's where our reactivity is, we might go through and say, oh, that's where my chemistry came in. So this nitrogen somehow came in and reacted with something like this to make the new bond structure. Does that make sense? Okay. Are there issues with that?
Yeah.
Why are there issues?
I don't know the exact reason, but shouldn't I saw it as like the triple bond would be with the nitrogen already before it came in.
So if we look at how I broke this down, and you're right, we're saying we're making that new bond. That new bond is a triple bond. How easy is it to make that bond?
Take like 3 steps.
That's going to take a lot of steps to make those 3 individual bonds. Okay, so it doesn't make sense that that bond is the new bond. Okay, so what we would have to then do is backtrack a little bit further away. So we're starting at our nitrogen. We don't have another direction out there, so we're going to continue to move in. Okay, if we're not looking at the triple bond, we're potentially looking at that bond. Okay, so now the question is, in that carbon-carbon bond, could we potentially see how that bond could be made or broken? So now what we're trying to decide is if that bond was to be made, what we need to do is think backwards what would happen if it the words are failing me. What we're going to do is take those electrons and they either have to go with this carbon, and I'll color code, with our red carbon or with the blue carbon. Okay, because what we're trying to do is reverse engineer this process. Okay, does that make sense? Understand roughly what I'm saying?
Yeah.
Somebody other than Devin? Yeah? So let's reverse engineer. Let's go through and say that those electrons went towards the blue carbon. Okay, and I'm drawing the rest of those pieces out, maintaining them. What we're saying is that that would then be our negative, and then the red carbon would have lost those electrons and would therefore be positive. Okay, why does that not make sense?
Well, we're doing a substitution reaction, right? That's what the beginning is.
Mm-hmm.
I agreed. But then you're either gonna, depending on which is it SM1 or SM2, then you're gonna need a nucleophile or a base. So it wouldn't make sense.
What does a nucleophile do?
It donates electrons. Oh, so that one could be the nucleophile.
So couldn't the blue one be a nucleophile? Yeah.
Yeah.
Would this then be an electrophile? Well, positive. Okay, yeah, it could. Remember, if we're going to run this, what we need to have is some kind of leaving group on our electrophilic species. Okay, so what we would have to do is now add a leaving group. What would be a good leaving group?
Oxygen.
Okay, we could look at oxygen.
Or
Why is oxygen going to be problematic? Oxygen also needs another bond. Okay. So if we're going to look for a leaving group, the simplest leaving group, the one that doesn't have any other secondary chemistry, would be our halogens. Whoops, as I try and draw with an eraser. Okay. That bromine could start to withdraw electrons, making that carbon positive. That's a potential. Okay. But then we would need a negative carbon here. Is it easy to get a hold of a negative carbon? No, why not? Okay. Small size, low electronegativity. Both those things contribute to the carbon not carrying a negative charge. Okay, but what we've got is at least a place to start. What was the other option we could have done?
Switch the charges. Who takes the electrons?
Switch our charges. Okay. So there's our nucleophile, there's our positive, right? Okay, but remember the positive species we wanted to attach to leaving group 2. So we'll replace that positive and we'll put on our leaving group. Okay. So now we've got the two most likely potential systems. The question becomes, which one do we like better than the other and why?
The bottom.
Why?
Because in the final product, you see that it switches the nitrogen thingy and the bromine. And it donates electrons to that carbon. I was talking about
So in your statement, I'm a little confused because
Well, that
identical
one.
systems.
I lost it. Are we looking for which one better acts as the nucleophile?
Yes and no.
What do you mean?
Okay. So when we're looking at trying to look at reactants, okay, or reverting backwards in this case, it is okay to say which one's a better nucleophile. We have to be a little bit careful with that because we're going to look at better nucleophile. This top one's probably the better nucleophile. How easy is it to make that?
Not easy.
Not easy at all. In fact, we don't have a way to make that. That should scream problematic for us. How easy is it to make this one? Pretty easy. We've seen that one actually show up before. What we're looking at is the cyanide molecule. That's a complex ion that exists already around. That has a standard existence. This one does not. Okay? So if we're comparing the blue structures, our nucleophile capabilities, okay, it makes much more sense to look at the bottom route because we're using a species that exists. That statement of that exists really only works if you've had experience seeing it. If you don't have experience seeing it, how would you know? That adds a whole nother layer of problems behind it, and there isn't a whole lot we can do to get around that. Okay? If we look at the red one, now what's going on? Okay, well, we've got a carbon with two very electronegative groups connected to it. Okay? On top of which, what's the hybridization of that carbon? Hold. It's got two groups of electrons, so it is?
It's just SP.
It's sp. Okay? And when we talk about running our substitution reactions, I believe we've talked about that for our hybridization, right? Should we address that? For our substitution reactions, what should the hybridization be on the carbon with the leaving group? Our substrate.
I don't think we talked about that.
Anybody remember?
Say SP.
It needs to be sp3 hybridized. If you go back and look at all the examples we've referenced, they've all been sp3 hybridized. Okay? We can use everybody's favorite thing when we looked at molecular orbitals and hybridization theory and all that. We can use that to explain why it's not fun, but we could do that. Okay? We don't have a good way of either stabilizing a forming carbocation, and we don't have a backside to run SN2. The backside of that carbon-bromine bond, I drew it kind of poorly. If this is sp, this is a linear structure. What's on the backside of the carbon-bromine bond? The triple bond, a whole bunch of electrons. So how could this nucleophile come in from the backside? All it's going to encounter is electrons, and therefore get repelled away. So the hybridization of that carbon negates the ability for it to react here. But why is it not a problem here?
Because it's attacking direct.
We've switched the attack. That carbon is sp3 hybridized. It can get to the backside now. Okay? Which, if these were our structures, which would we predict to be our mechanism? SN1 or SN2? Why SN2? Nate? Or do you have a different question? It's okay. Why do you want to say SN2? Why backside attack? Why is there no carbocation though? Does it show a carbocation?
No.
No, because I drew it. I've drawn the system that doesn't show a carbocation. Should I have drawn the system that showed a carbocation? Okay, that's a different question. Okay, and one that we should potentially think about and address, and we can look at that. Okay, what we backtracked out was those charges, and we said, oh, we needed a stable structure, we need the alkyl halide. Should the leaving group leave first? Okay, well, if it leaves first, it's leaving behind a positive carbon. Can that positive carbon be stabilized? Well, what kind of carbon is it? Is it primary, secondary, or tertiary?
That one's
Is zero-ary. Is a zero-ary carbocation good? Nope, that goes back to our SN1 dynamics, which would suggest no carbocation. Okay? What was the blue structure?
What do you mean?
What did it act as? A nucleophile. Is this a strong nucleophile or a weak nucleophile?
Wait, you said strong.
How is it strong? Why do we know it's strong?
Has a negative charge.
Negative charge. If it's a strong nucleophile, that would suggest SN2. So we're looking at backside. If I did a backside attack, what's the backside of the carbon-bromine bond? Electrons, which are blocked. Okay? So I don't like the formation of a carbocation because it's not stabilized. I don't like the backside. So no carbocation means no SN1. No backside means no SN2, which means
That one's not right.
there it is. It's wrong. I split it the wrong way. What happens if I split it the other way? Okay, I've got a negative carbon that's strong. Can it do backside? Well, what's the backside? Since that carbon is sp3 hybridized, it can come in from the backside. That's okay. Should I be forming a carbocation?
No, it happens.
I should do it all at once, not forming a carbocation. Why?
Because it would be on
If I formed the carbocation, what kind of carbocation would I form?
primary.
A primary. And primary carbocation stable? No. So I shouldn't form a primary carbocation, which means no SN1. I have a strong nucleophile, which means, or suggests, SN2. Do I have an open backside?
Yes.
Yes, primary is about as open as we get. That's two pieces of evidence that suggest an SN2 mechanism makes a lot of sense with these two reagents. So what should I put into my answers? I should put in that alkyl halide in red and that anion in blue. We then, sorry again?
Because I think it just asked for the
It technically asks for both, which of course is not going to let me do, depending on which one you draw. So there's two boxes here. So in this box, the correct answer that they've identified, and this could be a formatting thing, I would actually have to try and get in to try and break the question to see. Nobody, well, let's see. Nobody put in the wrong or put in the right answer. Ah, you. What was this, 23? I want to say it was 23. Nobody put in the correct answer for the cyanide, the CN minus for this first answer. So I can't see that, but that's what I would try and do, is I would try and put in CN minus to see if I could break it, to see if it was kicking back a wrong thing. If we click and look at the other one, we can see the view results and you can see the CNs. Okay. And there's the correct one, triple bond between the carbon and the nitrogen. We should be showing the negative charge on the carbon. How do you know all that? Well, that's how we broke the bond apart. We said the electrons need to go to that atom versus that atom. Kind of makes sense?
Yep.
Questions? Officially, that was for someone who couldn't make it to class. So. Other questions in general? Nope. Okay. So when we looked at the substrate effects, this is officially going to talk about it right here. When we ended and we looked at substrate effects, right? So we should be able to look at these and we should be able to roughly quickly classify them, primary, secondary, tertiary, all that fun stuff, okay, or zeroary. So this first one, the carbon is connected to 0 carbon, so I call that zeroary. Sane organic chemists call it methyl. Okay? If we move to the next one where our alkyl halide is located, so again, what our focal point is on our electronegative element. Okay? How does that electronegative element affect the structure? Because it's electronegative, it withdraws the electrons, creating a partial positive and a partial negative. Okay? So the chemistry that's happening is on our carbons where those halogens are connected. That carbon in the next structure is connected out to one other carbon, so we can call that primary. The next one's connected to 2 carbons, so we call that secondary. The last one where our carbon is located is connected out to 3 carbons, and we call that tertiary. So you should be able to relatively quickly find a reactive element, something that's electronegative. Our halogens stand out nicely for our substitution, but they can be oxygens as well. Start there and reflect back to that carbon and say, what is its classification? Because once you have a classification, you can now start to drop some mechanism information on it. Okay? Tertiary substrate has lots of carbons on the backbone. Those carbons, in comparison to a zeroary, hydrogens, have a whole lot more electrons, which means if the nucleophile tries to come in, the nucleophile donating electrons, it sees those electrons, turns tail, and goes away. What does that mean? SN2 doesn't work. So if you can look at your structure that has that electronegative element on it and quickly decide, oh, that's tertiary, you know you're not looking at an SN2 mechanism. That's a pretty quick screaming statement to throw out. Okay? And if it's tertiary, what could happen is the bromine could leave, forming a tertiary carbocation. A tertiary carbocation is relatively stable because those extra carbons can donate electrons weakly in, stabilizing the positive. Okay? If I formed a carbocation, I should now know that I'm looking at an SN1 mechanism. If we do the flip and look at the zeroary, the backside is very accessible. If the backside's very accessible, that suggests an SN2 is good. But by that backside being accessible, what I've done is removed electrons, which means the bromine is not likely to leave on its own. If it doesn't leave on its own, it can't form a carbocation, which means when I look at the SN1, not going to happen. So what I'm trying to do by applying out what these substrates are is evaluate relatively quickly to decide what mechanism is valid and what mechanism is invalid. What we will find, unfortunately, is that the secondary substrate works for both the SN2 and the SN1. Okay? So a secondary substrate should set off all sorts of alarm bells that you're now being asked to look somewhere else to differentiate between those two mechanisms. If you see a primary substrate, right away you know you're looking at SN2. And if we know we're looking at SN2, what should we be concerned about if we're asked to predict our products? It's a harder question. What do we know about our products for SN2? Reviewing notes isn't a bad idea. I like that. This would be in the complication category that I've specified. Perhaps phrasing the question a little bit differently, how many products? One product. Okay? If there's a chiral atom, what happened to it in the course of a SN2 reaction? When I say SN2, you say backside attack. So what happens to the chiral atom? It gets inverted. So those are complications, those are pieces that once you've identified its SN2, you have to know those repercussions, those secondary pieces that go with it. And if I see a tertiary substrate, I should immediately go up, that's doing SN1. And if it's doing SN1, what are the repercussions or the complications that I would expect there? Loss of stereochemistry, which means I get two possible products. Right? And I would have to ensure that those two possible products were either different from each other or identical. If they're identical, I only look at one product and I don't care. If they're different, then I have to specify both because I have a loss. Make sense? Okay. These are looking at hybridizations for the carbon being sp3 hybridized all the way through. Okay. The sp3 hybridization is the standard hybridization for our substitution reactions or our straightforward one. Okay. What happens if we switched it up and instead of looking at sp3 hybridized, we made the carbon where our leaving group was. So again, for each of these, what we're doing is looking at, there's an electronegative, electronegative, and electronegative, and what we're concerned about is the carbon where that electronegative element is connected, because that's going to drive the chemistry. And if we look at the middle one, that hybridization is sp2. Okay? And it turns out that sp2 hybridization drastically changes the chemistry of that bond. Okay? Well, how does it change it? Well, sp3 versus sp2. Okay? This floated real quickly by when we talked about hybridizations, and I said this was something that was an effect, okay, that you probably don't need to stress a whole lot about, but this is where one of the places where it manifests. sp3 is more hybridized because it's hybridizing all the orbitals. sp2 is hybridizing less. The less hybridized, the closer the electrons are to the element. Is there a way to reference kind of the ability for an atom to hold electrons closer? Electronegativity. And when we look at this sp2 hybrid, the electronegativity has increased, which means this bond is now less polar. That bromine is less willing to take the electrons than it is in the sp3 cases. Okay? What you can do is just say, well, dang, that's an sp2 carbon. How do sp2 carbons react in either SN1 or SN2? They don't. That's all you need to know. Okay? If we look at the top and the bottom case, those aren't sp2. Okay? Well, why do we care about those? Well, how is that top one different from the primary that we showed on the previous slide? Right? Here's our primary. How is that primary substrate different than this top primary substrate? We have a pi bond. Does that pi bond matter?
Yes.
Yes. Why?
It makes it a little.
Ooh, it makes it allylic. Why does that matter?
Because that is not reactive in SN1.
Other way.
Allows for resonance. It is reactive in SN2.
Okay. If we look at an SN1 mechanism, what happens? The leaving group leaves first, forming that primary carbocation. That was weird. And when we looked at the previous substrate where we had the chloride on there, we said that that reaction doesn't work because what we end up forming is a primary carbocation. And primary carbocations don't have the electron density to stabilize that positive. If we look at, as you stated, the allylic one, our top case, isn't that also a primary carbocation? Yes, so shouldn't it also not react in an SN1?
Yeah.
That's a perfectly awesome and valid assumption, except that when we test it, it does react. If it is reacting in an SN1, what does that mean about the carbocation?
There's resonance.
It must be stabilized. It's not being stabilized by the substitution pattern. Are there other ways that you could stabilize a positive? Yes, you could stabilize through resonance. That resonance effectively reduces the positive charge on any individual atom that holds the charge. So now it's not +1, it's +0.5, because I'm spreading that positive charge now across 2 individual molecules for that resonance. That's an insanely stabilizing factor. Right? If we think to our reactivity list, we start with charge, we move to size, we move to electronegativity, we move to resonance, we move to induction. Where in that list have I mentioned primary, secondary, tertiary? I haven't. But we're using primary, secondary, and tertiary to explain all these stabilities. That's because in the examples that we're looking at, that's the only difference. Does that difference change the reactivity? Yes, absolutely. Then why is it not in the list? It is. It's in the last thing after induction. The, oh my God, please don't ask me a question about this because there's so many different things that show up here. Yeah, that's the substitution pattern. Resonance is significantly higher up on the list. It stabilizes much better than primary, secondary, and tertiary. So that when we look at our reactivity summary for SN1, we would expect tertiary, fancy word allylic, means resonance. Tertiary with resonance to react faster than secondary with resonance, faster than primary with resonance, faster than tertiary, faster than secondary. Primary is not on the list because primary is just not stable. Primary with resonance is on the list because the resonance stabilizes it. Kind of, sort of? How does it affect SN2? When I say SN2, you say backside attack. Is the resonance doing really anything to that backside?
No.
So does it matter? No. That resonance really only comes into play after the leaving group has left. In SN2, the leaving group doesn't leave first, so the nucleophile has to come in. You could make an argument that that nucleophile is now butting up against those electrons. You can make some other molecular orbital arguments. But for the most part, for what we care about in this class, in SN2, there is no resonance effect, number one, okay, because we never form a carbocation. And number two, the steric effect or hyperconjugation or whatever fancy words you want to throw at it is such a minimal effect it isn't worth your stress to worry about. So what's the deal with the allylic, tertiary allylic, secondary allylic, primary allylic? It isn't. It's tertiary, secondary, or primary. And for SN2, primary reacts faster than secondary. Tertiary didn't react at all. Whether it was allylic or not is irrelevant because I don't care about the resonance. Make sense? Cool. Okay. The repercussions of our different mechanisms. What happens in the SN1 if we were to add curved arrows to this?
You talking about the SN1?
Yep, so the top reaction.
Oh,
Leaving group leaves. That ring we can sometimes abbreviate as pH. Have we seen that yet? No. Sometimes people do that, sometimes people don't. I do it because I'm lazy and I don't want to draw the ring out. I don't think you have that shortcut in active, so I wouldn't stress about it. But you might see me write pHs. I try to not do that on exams. If the chlorine left, it left with the electrons, which then means
what's next?
The chlorine is negative, and I get a carbocation. Okay? That carbon is no longer chiral. Okay, so I don't need to specify wedges or dashes. But now what can happen? The iodide could come in and react. What is it reacting with? What is the carbocation? Where is the carbocation? Yes, it's on that carbon, but where?
What?
We've had this conversation.
I don't understand the question.
It's on a p orbital.
Oh.
Why is that a big deal? Where's the p orbital? In this drawing, it's coming out at you and going behind the plane of the paper, which means the iodine can come in and come out at you, or it can come in from behind, which then means what happens?
There's two.
You get two products. Okay, which I'm being lazy about and not drawing the structure. Should I draw the structure? You just laughed at me. Fine, jerk. So you would get both of those products. We call this a loss of stereochemistry because if we go through and assign stereochemistry, iodine is 1, the phenyl is going to be a 2, 3, our CH3 in the back is 4, 1, 2, 3, I'm rotating counterclockwise, thank you. 1, 2, 3, I'm rotating counterclockwise, but my lowest priority is aimed at me, which means I have to invert it. S goes to R, I get an R and an S. The net result is a loss of stereochemistry. Okay, so that was one of our big repercussions. In the SN2, what happens? The nucleophile has to come in from the back side to force the leaving group out. Okay, what is the back side of that bond? Well, it's going to be dashed iodine, and then it's going to force that methyl group up. If we go through and assign, I don't know why I drew that as a negative, apologize. That's I. 1, 2, I don't know why I'm numbering that one. It's a dumb one to number because we already know that one's S. 1, 2, buckle my shoe. 3, 4, 1 to 2. That's what happens. Why am I making a frowny face?
Because
1 to 2 to 3 means I'm moving which direction?
clockwise.
Clockwise, which means R, but
The iodine is
the highest priority is aimed at us, which means the actual assessment is S. But if we did inversion, shouldn't it have flipped? It's because I drew the structure wrong, and this is where it's really important to have a drawing pattern behind it, and I tried to get too fancy behind the drawing pattern, and I screwed it up. Okay. Backside, iodine, we push the methyl forward. Now if we go through and assign 1, 2, 3, that's 4. 1, 2, 3, we're moving counterclockwise, we're looking at it backwards. Goes to R and we got inversion. Okay. What I was attempting to do had to do with the different alignments to ensure that we get our product as easily as possible depending on our orientations. If you're seeing your leaving group wedged, maintain the geometry of everything, except put your nucleophile in dashed. What was dashed make wedged. That's what I drew here. Okay. The SN1 becomes less of an issue because you get to pick how you draw those out, and there's less of a dynamic behind it. But if we set this up where we do, let's do it this way. I'm gonna ignore stereochemistry because I don't want to assign this one. I may have to assign this one. If our iodine comes in and attacks, how should I draw this?
In the plane of the paper?
Yep, all of this is happening in the plane of the paper, so the iodine I'm showing coming in as a solid line in the plane of the paper up away from it. What happens to the rest? Those just push down away from it. Did this set me up with an inversion? Yep, of course I have to go through and number it. 1, 2, 3. There's my 4, 1 to 2 to 3. Which direction am I moving? Clockwise, so that one's R. We look at the product, 1 to 2 to 3 to 4. Which direction am I moving? Counterclockwise, it's S. Lowest priority was maintained in the same direction each time. Do you see what just happened there? Because that's a bit of a challenge. If we have the leaving group on our wedge or dash, we effectively maintain the exact orientation of everything. If we have the leaving group in the plane of the paper, now where we're showing is where the nucleophile actually came in. A little bit more explicitly, a little bit better drawn. Okay? You'll get the exact same result. You just have to be very careful with how you draw the alignment of those pieces. If you're in a situation where it's a short answer, okay, pick a directionality that works for you. How do you know it works? You've practiced it a bunch and you're comfortable with how that drawing works. Okay, so that when you get to the exam, you're following that same process. If you're looking at a multiple choice, the multiple choice will have all of these drawn out for you. What's your best way to ensure you've inverted? Probably going through and labeling R and S. Okay, that's probably going to be the easiest approach. Okay, that means you should be relatively fluid, assigning priorities, speed with all that. Make sense? Okay. Okay. SN1, this is just another way to kind of try and visualize it. So if we're looking at the structure, and I keep asking though, what is it reacting with? It's reacting with the carbocation, which is a p orbital. That's dealing with our hybridization. Okay? If we try to draw that p orbital, it's going to be really hard to see because it's coming in and out of the plane. But if I take that three-dimensional molecule and I now just turn it, okay, because this is all planar, and I turn it out of the plane, now where's my p orbital? Now I can see it on either side of that alleged mirror. I don't know what that blue thing's supposed to be. Potentially the plane of the molecule. We have our p orbitals on either side, which means the iodine can come in from either side, producing two different products. Okay? Those pictures should theoretically align to that orientation, and they don't necessarily, but that's what they're attempting to show. Does that make sense? Okay, so it's really just trying to reanimate what we've already talked through now several times over. Okay, and then our SN2, this is the one where we talk about an umbrella. Okay, if we look at this as kind of an umbrella, our nucleophile is coming in from the back side. It's coming in from this side, effectively a wind gust behind it. What happens is the rest of the umbrella has to flip the other direction away from it. Okay? And that's the kind of umbrella analogy behind this. Okay? Officially, it does not require that you invert stereochemistry. Typically, it does. Okay, so memorizing that you get inversion of stereochemistry is perfectly acceptable, particularly for the sake of the class, but you can find scenarios where it's not technically inverting the stereochemistry because it is independent of stereochemistry. Stereochemistry is assigning all the different priorities. Okay, it just happens that it aligns the vast majority of the time. Okay? Carbocations, this is dealing with the rearrangements. I'm fairly confident there are no rearrangement questions on the exam, so we'll talk through this really quickly, just in case you see it. We had our carbocations. Which one was the most stable? Tertiary was the most stable. What happens if you go through and run a reaction where you form a secondary? Because you can't form zero area primary. If you run a reaction where you form a secondary, it can come into existence. That's perfectly allowed. Right? But that's very low on the stability scale. Okay? So what our structure will try to do is rearrange the atoms around it so that it can make a more stable carbocation. That rearranging of atoms, kind of understandably, is called a rearrangement. So if I somehow formed a system where I formed a secondary carbocation, and I look next door, and there's 3, say, carbon atoms next to it, what I could do is I could take the electrons in that bond with the atom, and I could move it. What happens? Now my carbocation is going to appear at a different spot. If this is a tertiary carbocation, this is more stable. So the structure will do it. Okay? It's looking within the molecule to stabilize. Okay? There are varying driving forces that push them. Usually it's going from secondary to tertiary, okay, as far as stabilization. Okay? It's very, very local though. So when we're looking at this system, it is one bond, there it is. Can I move those? Depending on what atom you'll move, you'll hear different names. You'll go, oh, we're looking at a 1,2 hydride shift. Of course it's 1,2. What we're referencing is where the carbocation is and the very next atom. Okay, when we say 1,2, what we're doing is we're taking an atom at the 2 position and moving it to the 1 position. Okay, so if we say a 1,2 hydride shift, what did we move? Hydrogen. If I say a 1,2 methyl shift, what did I move? A carbon. If I say a 1,2 phenyl shift, what did I move?
Is that the ring thing?
The whole honkin' ring thing. Okay? All we're really doing is moving the electrons in the bond. I don't care what this thing is out here. Okay? It can be absolutely ginormous. All we're talking about doing is moving those electrons from this space to that space. It is a very short hop in distance, and everybody tends to freak out about the size of the things moving. The size of the thing is tiny. It's electrons here versus electrons. You're taking these 2 electrons, and instead of putting them there, you're putting them there. That's a very small space to move. Okay? The shift itself, whatever atom you're shifting, people will associate different names with. Okay? Those shifts, secondary to tertiary usually works, and then you can also see it with rings. Like a 3-membered ring is very, very stressed. If there's a carbocation next door, the ring can break open to form a 4-membered ring. Okay? It may not change the carbocation energy necessarily, but what it does is change the overall energy of the molecule because you went from 3 to 4. Okay? So you can see things like that. Like I said, I don't think I'm going to ask anything about them. Okay? Which is exciting because a big white space means
You're done?
we're done with substitution. Not done. Now we got to deal with elimination. Okay? So let's backtrack out and do more of an overview of an elimination. Actually, let's do substitution. How do we do a substitution reaction?
Replace a non-hydrogen atom with a non-hydrogen atom.
Replace non-hydrogen with non-hydrogen. So, give me a structure. Right? There's a structure. Okay, and what do we react it with? We need to replace it with a non-hydrogen thing. Okay, what non-hydrogen thing do you want to replace it with?
Iodine?
Okay. Iodine, I2. No. What is the characteristic of the thing you're going to replace? It needs to be negatively charged. What we're looking at is not iodine, but iodide, negative. Okay? This runs a chemical reaction where it replaces iodine and then our bromine. Sorry, bromide. I want to yell at you for your naming. I should fix mine. Okay, cool. We've done that. Okay, that's what a substitution reaction looks like. Okay, what changed? The bromine left, which means the bromine is, I did it again, our bromide. If we look at it as a class of things that take electrons from our molecule, we could call it a leaving group. What did it leave from? Our carbon structure. What was the name that we give to our carbon structure?
Oh, substrate.
Our substrate. The iodine donated electrons, which means it was. And all of this reaction took place in a solvent.
Oh.
So when we talked about our substitution, we had to acknowledge what were the changes, when those changes happened, and then how did the substrate affect that change? How did the nucleophile affect that change? How did the solvent affect that change? How did the leaving group affect that change? Okay? What happens if instead of this being a substitution, it was an elimination? Okay? In an elimination reaction, we have a pi bond formed. And 2 sigma bonds broken. Okay? If we now go through and look at our overall reaction, well, some things need to change. Number one, need a pi bond. It's going to be pretty important. But if I drop in that pi bond, what else had to have happened? The bromine had to leave. Is the iodine connected? Nope. So that's a modification from our substitution. Okay? And you made an important point. You referenced the hydrogen. Actually, I'm going to use this. Okay? So if we look to getting to end with our blue structure, okay, officially there's another hydrogen there for the record, right? We've lost a hydrogen from that molecule, and the bromine has been lost from that molecule. Okay? The electrons to make the pi bond come from the bond with the hydrogen. That's why I'm showing that in red. Why did they come from the bond with the hydrogen? What did the bromine do? It took electrons, which then means I don't have any electrons to make a pi bond. That's why we take them from the hydrogen. How reactive is that carbon-hydrogen bond? Not very reactive at all. Okay, how is it? Why do you know it's not very reactive?
It's
Non-polar bond. So if we pull back from those terms and definitions that we use early on, it can help us predict these things. Okay, so how could I help to break that bond? What would that substrate be acting as? It's taking electrons away from the hydrogen to form H+, which means what did this molecule act as? It produces H+. So if I look at another reaction that produces H+, let's say HCl. What did HCl act as? It's an acid. What is this molecule acting as? An acid. What do acids react with? Bases. Not a nucleophile now, because if it's a nucleophile, it's going to react with the carbon. Okay, what I need this species in red to do is to react with that hydrogen, which means this species in red is still going to need to donate electrons to that hydrogen, But since it's picking up a hydrogen, it needs to act as a base. I minus is not a good base. Why is it not a good base?
Because it's large.
Yeah, it's large. Because it's large, it can't stabilize, or it stabilizes the electrons really, really well. If it stabilizes the electrons, those aren't likely to react. Cool. So what would be a good base? You spent at least a semester where you worked with this base.
Oh,
Like sodium hydroxide?
yeah.
Yeah, there you go. That would work. And we'll nuance that and drill into the base. Okay? So if we look, really what changed? Do we still have a substrate? Yes. Do we still have a species that's donating electrons?
Yeah.
Yes, but it's changing where it's donating electrons. It's changing because it's donating electrons to a hydrogen, not to the carbon. Okay? We're forming a pi bond. So that's a little bit different. We still have a leaving group. Okay? And officially, we don't have that just H+, we'd have that reacting with our base. Okay? So we still have the same core pieces, which is both a good thing and a bad thing. Why do you think it's a good thing?
Because you know them already?
We already know all these pieces, so we don't have that much more work to do because it's the same fundamental pieces. I just now am applying it to a slightly different chemical reaction. Why is it a bad thing?
Because it could be confusing.
All of those pieces are now so similar to each other, you have to be able to nitpick and differentiate why one does one thing and the other does another. Okay? So you have to be really refined into each of those pieces to know what's going on. Double-edged sword. Yay. So, what did the 1 mean in SN1? That was a horrible question, because you don't need to know that. Okay? When we said SN1, what does that mean? Carbocation. When we say E1, what does that mean? Carbocation. What does 1 mean? Carbocation. Okay? So that 1 is suggesting that we need to form the carbocation. So all of those things that we did for SN1, for substrates, we want tertiary substrate. Why? Stabilize carbocation. Guess what? If you think you're doing an E1 reaction, same deal. You need a tertiary substrate. Okay? Leaving group, still got to be good. Okay? Here's where we introduce an issue. Base. Okay? The base donates electrons to a hydrogen. What did the nucleophile do? Donate electrons to not hydrogen. So they are fundamentally the same thing. It's just a question of where they are donating their electrons. So before we even look at this weak but heat is good, what we really need to do is be able to differentiate base versus nucleophile. Conveniently, you watched a video last week that discussed the difference between bases and nucleophiles. Do you have questions about that we should potentially review? Do these have, since you don't have questions, do these have different base nucleophile characteristics? 2 molecules. Yes. How are they different?
One's attached to carbon, one's attached to nitrogen.
How are they different as far as base versus nucleophile?
The top one can give up electrons.
So can the bottom one. They are both negatively charged. So if we're looking at reactivity, charge size, it's not enough to make any effect. What this gets at is the difference between a nucleophile and a base. What is a nucleophile?
Something that donates electrons to not hydrogen.
Where is not hydrogen? That's a stupid question, Mike. It's wherever there aren't hydrogens. Okay, okay. What is a base?
H plus.
An H plus acceptor
Yes.
by doing what?
By donating electrons to H plus.
Where is H plus?
Where the hydrogen is.
Where the hydrogens are, Mike. This is stupid. I still don't get it. I picked way too large of a molecule. I should have pitched a much smaller molecule. Where are the hydrogens on this molecule?
On the outside of the carbon chain.
Where are the not hydrogens?
On the inside.
On the inside. So if we consider looking at an individual molecule, what we've got is all the not hydrogens in the middle, and we have all the hydrogens on the outside. Okay? Death Star-like. Okay? For a nucleophile to react on the inside, it has to get past the hydrogen, the outer defenses. Okay? So can like a battleship attack the Death Star successfully? No one's seen Star Wars?
I'm just not good with the analogies.
That's just bullshit. Stupid class. Star Wars.
No?
No, Battleship can't, because it tries to get at the outside and the blast and guns and all that fun stuff. Okay? The only hope to destroy the Death Star is to take a small X-Fighter to launch a little bomb right at the very edge on the inside, but it has to get past all that outer stuff. So it has to be small enough to get in to drop the bomb. If it's too big, the outer defenses just destroy it. So if we're looking at a nucleophile, that's got to be small to get past the outer defenses. A base doesn't need to be small, because what's it reacting with?
The hydrogen.
Everything on the outside. So when I now go back and look at these molecules, what's the difference? This one has carbons, that one just has a hydrogen. This one is
Big.
big, this one is
Small.
small. And if it's big,
Base.
it's likely to act as a base. Why won't it act as a nucleophile?
It has a harder time getting to the inside.
It's so big it can't get past the hydrogens. It ends up reacting with the hydrogens before it can get to the inside. Because this one is smaller, what can it do?
Get to the inside.
It can get to the inside. Does that mean it doesn't react on the outside?
Not necessarily.
Unfortunately, no. Okay? If it's small, it can act both as a nucleophile, it can get to the inside, and it can act as a base and react on the surface. If it's big, it can only react on the surface. Why does that become important? Right? Well, in our summary, we said the difference between substitution and elimination was either nucleophile or base. If I want to do an elimination, that species that donates the electrons, what might I expect or want it to be if I want an elimination, not a substitution? I want whatever that negative thing is to be big. Okay? That bigger thing now changes the dynamic where it can't act as a nucleophile, and it limits it. Okay? If we're looking at the E1, just like the SN1, that red thing isn't a big deal. Okay? So it can be weak. Well, how do we know the difference between weak and strong?
Charge.
Yeah, charge. If it's negative, it's strong. If it's not negative, it's weak. Keep it simple. Okay? So when we're looking at that, okay, I still have to break that hydrogen off. And if I'm using a weak base, that's not super likely. Okay, so how else could I break that off? All I do is heat it up. What happens when I heat things up?
Molecules
They move faster. You mean each of the bonds vibrate. So if I've got a bond between a carbon and hydrogen, that's a strong bond, and if I add enough energy, it starts to vibrate until eventually it breaks. Once it's broken, the electrons can immediately come in, form the carbocation, and now the hydrogen is like, well, what the hell? Right? And it's lost its partner. Right? So in an E1, we're still looking at this base issue. We've got to be a little nervous with it. It's not as big of an issue as it is for the E2, but one of the things that we'll tend to see is heat come into play with eliminations. How do we see heat in a chemical reaction? Okay? There's two ways to see it. Okay? Literally written as heat. Okay? Arguably there's three ways. Okay? Heat. Yes, I'm adding heat. Okay, what's the other way? Yeah, that little triangle. That delta symbol for change in temperature. We're adding heat. Okay, that's what that's supposed to represent. The third way, which isn't actually shown there, an actual temperature. Okay? What is adding heat as far as an actual temperature? Is it not room temperature? Is it higher than room temperature? You're adding heat. Okay? The worst example I have ever seen was a reaction being like, yeah, we're adding heat. Like, you are just being a jerk. Because what's room temperature? 25 degrees Celsius. Yes, you are technically adding heat. You've added 5 degrees temperature difference. Okay, that's a bit rude. Okay, usually it's either heat or delta symbol. Those are giant red flags that you're looking at an elimination reaction because you're trying to vibrate that bond off, that carbon-hydrogen bond that is not easy to break. Okay? After that, you've got your solvent. This does say polar protic. For the elimination reactions, the solvent is misleading. Okay? Polar protic absolutely is true for an E1. It is. Okay? It's just misleading. So generally, I don't recommend associating or using the solvent to say I'm doing an elimination reaction. Okay? I would ignore that. Okay? Next kind of fun part that we get out of this is this fancy word called regiochemistry. Regiochemistry is referencing where the chemistry is happening. Okay? And the structure shown up here actually allows us to dictate some regiochemistry. It also sort of gives us stereochemistry. If we take a look at the products here, what's the difference between those products?
The shift of sigma bond,
Say it again?
where the sigma bond is located on the carbon.
Yeah, I don't like that explanation. It's not horrible, but I don't like that explanation. What's the difference between those products? Say it again? The rotation of... It's not the sigma bond that's rotating. It's the pi bond. So it's how you made the pi bond. In one case, you made the pi bond where those sigma bonds were on the same side, whereas you made the pi bond over here where they were on opposite sides. Because once it's been formed, you can't rotate. So this has to do with the internal dynamics of our reaction. This is producing cis versus trans. This could be referenced as stereochemistry. And if we're talking about doing that, what we're talking about doing is referencing or removing either the red hydrogen or the blue hydrogen. I don't know which one's which, to be honest, and I don't think you need to know that. Okay? But depending on which of those hydrogens we remove, we either get cis or trans. Okay? Because we're forming a carbocation, what we want to do is form the most stable product possible. Which of those products is more stable? Cis or trans? Neither doesn't, is a little weird. Should they have a different energy? Yeah. Why is their energy different?
Because the electrons
What electrons?
are around
Sure.
Okay. Yeah.
Those sigma bonds are electrons. Those electrons are located on the same side, so they are close to each other. What are they over here?
Opposite sides.
They are further away from each other. Which is more stable?
The one that's further away.
Further away from each other is more stable. Our trans is by far the more stable product. And when we run our eliminations, we almost uniformly get trans products. Can cis still form? Yes, absolutely, but the trans is the higher favored product because it is more stable. Okay? This is kind of a stereochemistry issue. Okay? When we go through and do this, we're removing the hydrogens that are one carbon away from where our leaving group was, or where our carbocation is. The name on that, for whatever reason, I don't know why they labeled it this way, is beta. So if you're looking at other videos, you might hear something about beta elimination. That's just a standard elimination reaction. What are we talking about doing? We're removing a hydrogen from the beta position to where the leaving group was. That's a beta elimination. Okay? So beta just means one carbon away from where our carbocation is. How many beta positions are there? Where's the second one? The other hydrogen is at the same beta position, so that's not 2.
The one down.
There's nothing that says I have to name upwards for my beta. I could name downwards as well. Is there a hydrogen there?
Yeah.
What would my product be then?
The formation of pi bond.
Okay. This is regiochemistry. Where did the double bond form? Okay. Cis versus trans is our stereochemistry. Regiochemistry is what atom is actually reacting. We're looking at a different atom react. Okay. So is there a preference? Okay. Well, now what we introduce is other concepts to our stability. Here we talked about the stability of trans being more stable than cis because the electrons are farther away from each other. Okay. Well, what do you think about this one? This one would be referenced as terminal. Should this be more or less stable than those? And this becomes a harder question to deal with. Okay? It's less stable. And what the stability has to do to, or the way that I like to reference the stability, is what makes all of those reactive. Are pi electrons. So if we're looking at the alkene, how does it react? Those pi electrons come out and they would donate to something. Okay, that's looking at their reactivity. If I look at that orange one, what are those electrons trying to get by? They're trying to get by a hydrogen. Well, hydrogen's pretty small, so that's a pretty easy pass. Goes this way, trying to get past a hydrogen. That's a pretty easy pass. Pretty easy pass. Oh, that's kind of hard. So if I look at that structure, I say effectively 3 routes are easy. What happens if I go up to the trans?
2 routes.
So what does that mean towards the stability?
More stable.
The trans is more stable than the terminal because it has fewer routes for reactivity. Make sense? The official terminology that goes with this goes back to the same terminology that we would use from our primary, secondary, tertiary, or similar to it. It's the substitution. Okay, so let's clean up all those stupid arrows. We would reference that orange one as mono-substituted. What does mono mean? 1. What's the substitution referring to?
Where the electrons come in.
That 1 carbon. Trans is di-substituted. Because
2.
what is the highest value that we could reference when we're looking at our pi bonds? We have mono is 1, di is 2. What we're referencing is the 4 positions, the 4 atoms connected to our carbons of our alkene. If those atoms are not hydrogen, we can reference those as a substitution pattern. Mono substitute is the most reactive, okay, or the least stable because of that route method that I would call. Okay? Di substituted is more stable than mono substituted. What's more stable than di substituted? Tri substituted, which means I have 3 carbons on it. And then tetra would be the most stable. Okay? Those substitution patterns, and I think I mislabeled regiochemistry here. Okay? The logic of saying more substitution is where you'll hear reference to something known as Zaitsev. We want the most stable double bond possible. That means more substitute. This guy, before the existence of electrons, was able to say, this is a rule. When we do eliminations, we make more substituted pi bonds. Barely understands chemistry and is able to make this conclusion. That's why he's popular and why he's named. Okay? I would argue we know about electrons. We don't need to memorize some old dead guy. Okay? I don't think that's necessary. Okay? But you will hear reference to Zaitsev and anti-Zaitsev, okay, in chemical reactions, particularly if you're looking online. Okay? Benefits is a bit problematic because none of these statements for our E1 are benefits. Rearrangements are possible. You formed a carbocation. Carbocations can rearrange. That can make things a whole hell of a lot more complicated. Okay? And if we look at the E1, everything about it aligns with the SN1. Okay? Which means if you're looking at a reaction, go, oh, I think that's SN1. Guess what it also is? E1. Which means when you run an E1 reaction, you get SN1 products. When you run an SN1 reaction, you get E1 products. There's very few ways you can limit it, and that limitation comes in right there. Heat is pretty much the only signifier that you can add to a reaction to help ensure that you're getting an elimination. If you keep the reaction cold, maybe you can limit the presence of the E1. How do you know it's cold? Doesn't say the word heat. That's a good thing to do. Okay? If it says cold, that's another signifier if it's cold. If it says negative 78 degrees Celsius, that's flipping cold. Okay? So those things can sometimes go with your substitution reactions to help kind of push those out. Typically what you're looking for is, do I see heat? Now I'm looking good at elimination. If I don't see heat, I'm probably doing substitution. Kind of, sort of? We'll pick up with, I think E2 becomes the next one. Yep, our next big summary. On Thursday, there are not very many more slides. After E2, we're now looking at how we compare E1 to E2, then how we put it all together, SN1, SN2, E1, E2, and decide which one of those reactions we get. At that point, there's some summary things to help kind of memorize you, or that you could use to memorize. And I'm advancing slides like crazy and nothing's happening because that's it. Okay, I would imagine we get through those slides relatively easily on Thursday, which then means we're just left for practice. Our exam is next Thursday. Hooray!